plan for today is open house gossip. No. We're going to listen to one more paper that uses regression, and we're going to pay attention to whatever interesting things they do there, and then talk about them if needed more. And we're going to play with something fun, I hope, again in R. I hope you brought a device. I left off class last time by violating regression assumptions and making you all mad, hopefully, because I was doing something illegal, and I promised I would fix it today. So I'm planning on doing exactly that. I'm gonna fix it. Okay. Has anybody worked on homework yet? Or decided on questions? Please tell me, I'm very curious. What are you asking? Anyone?
Oh, I haven't sorted it yet, so I don't know what to ask.
Okay. No, I mean, what questions are you asking off that data set? Has anybody thought of questions?
We kind of try to see the difference between computer science and other departments.
Yeah.
But we are still kind of analyzing.
Okay. Yeah. You're all...
is hard. I think that's the biggest issue, at least for me. It's easier to do things in Python instead of R.
Okay.
So it's like...
So good advice to people with similar experience. I was like this. I prefer to do all of my data manipulation in Python. Collecting, scraping, curating, organizing, all of this data manipulation stuff I usually do in Python. I'm more used to doing it that way, and I find it easier. And then I basically have data frames or tables or something that I analyze, and I do all my statistics in R, because usually the support for stats and interesting analyses is better in R than in Python. Sounds good.
My friend did a workshop paper on sex differences in computing. So I kind of want to just run all of their analyses on the CMU data.
Cool.
Questions were basically, is the sex of computer science instructors correlated with average teaching evaluation scores? They also wanted to see the difference between professors and students, instructors, and
interesting.
computing and non-computing instructors. So I will try to just replicate what they did on our data, and then probably ask some other questions as well.
Sounds good. Pay attention to controlling for relevant covariates, like amount of teaching experience and whatever else. Whether the class is co-instructors or single instructors, and who knows what else may make a difference, and incorporate those in your analysis. Anybody else thought about questions? Do you have something you were asking? You're thinking of asking? Not yet. Okay. No. Anyone else? Questions? I'm collecting ideas. No, it's fine. I'm very excited about this and generally very curious. So that's why I'm asking. Yeah.
One of the things I think I might look at is, as part of the literature review, I read about this theory where it's not necessarily based on better ratings based on sex, but it's based on the gender makeup of the department, or not necessarily gender, but if you're in the minority, or sorry, if you're in the majority, you're more likely to get a higher rating.
Yeah.
Because of the expectations.
Can you scrape additional data from somewhere else to calculate some variable that gives you a sense of how diverse the department is?
Maybe.
Look for it. I think CMU has some.
There is
data about it. Yeah.
Like department level or something?
And it's not in the data set.
Probably not.
Where do you find this?
I remember reading it for the literature review, but I can try it.
It's easy to find.
Is Google?
Yeah, it's CMU department of graphics. And there's a web page where you can actually do kind of high level analysis. Generate graphs and stuff.
Okay, yeah.
So, by the way, if any one of you ends up collecting additional data from a different source and enhancing the data set I shared, you may want to also share it with others. Maybe there's other questions folks are interested in asking using your additional variables and whatnot. No problem with doing that, sharing the data. Is anybody looking at 8 a.m. courses or something? So a personal pet peeve, I hate waking up early. Maybe if somebody gets interested, I would be very curious to find the answer to that question. All right, so Claudia is going to tell us about another regression paper and then hands-on our stuff. Sound good?
Okay, there are some things that I didn't understand in this paper, and I have question marks all over the slides. So I will talk about the Twitter predicts citation rates of ecological research. And just to give you a little bit of context, usually researchers produce papers, and usually they use the H index as a metric for success. And essentially, this metric takes into consideration both the research output, so the number of publications, and also the research impact of said papers. And there are two ways of measuring this research impact. Usually, we go for citation rates, but there are also alternative metrics that we're going to look a little bit more. So the problem, okay, one went away. No problem. The problem is prior work reported low correlation between traditional citation rates and alternative metrics, but it is not clear if it's because the alternative metrics are an imprecise measure of research impact or if they just operate independently of citation rates. So what they try to do in this paper is, besides considering only the alternative metrics, for example, Twitter activity, they also try to look into some confounding variables. And in a potential cause-effect relationship, a confounding variable is a third-party variable that influences both the cause and the supposed effect. So what the authors try to do here is estimate the effects of Twitter activity, so the alternative metrics, on the citation rates, focusing specifically on ecologic research articles, while taking into consideration effects like time since publication and 5-year impact factors. And what they try to do as a methodology, they collected articles from different ecological journals, and they focused on those having impact factors superior to 3. So the idea is to reduce and lower the zero inflation in the distribution of citations. So if they had a lot of articles with 0 citations, they would exclude them. And also they want to lower unwanted variations caused by discipline-specific differences. So they argue that some journals, like they are more specific for a specific discipline, so they will have very specific types of articles, and they want to lower that because usually there are fewer people interested in specifics. And they randomly selected 3 articles from each issue of each journal, and the idea is to increase generalizability of the results. And then they focused only on primary research articles, and the idea is to lower the bias caused by article type. For example, if there were opinion pieces, they would try to exclude them because in theory, those will trigger more opinions on social media. So for each article, they ended up collecting the number of citations, which they collected from Web of Science. They also collected Twitter activity metrics, which are our alternative metrics. And those include the number of tweets associated with each article, the number of users tweeting, and also the reach. And they also collected time since publication and the impact factor of the journal. Here in the blue ones are the confounding variables, which I believe we can call them the mediators. I'm not sure. Okay. And before diving into the linear regressions, they first did some pre-processing. So they looked for evidences of nonlinear relationships or by model patterns, and they didn't find them. So they didn't have to include quadratic terms in the models. They also address multicollinearity by removing variables and the criteria was looking for high correlated variables, and they ended up deciding to keep the one that made more sense to them. So they kept number of tweets instead of number of users, for example. And they looked into the standardized variables, the z-scored we discussed the previous class, which essentially allows them to compare effect sizes across predictors on a common scale. Regarding the statistical analysis, they use generalized linear mixed models. And from what I understood, this is like a linear regression in which they also take into consideration random effects. And they added the journal identity as a random effect to account for the fact that some of the articles are nested within journals, and the idea is to try to remove these differences that may happen just because of the journal. And then they modeled citation rates as random variables of a negative binomial distribution. I'm not quite sure what this means. And they looked both into statistical significances. So they were trying to determine if a predictor has a significant effect on the dependent variable or not. And they also looked into relative importance, which allows them to quantify the influence of each predictor on the dependent variable. So when it comes to results, first, we can conclude that the 5-year impact factor and the Twitter reach do not significantly impact citation rates. So those values are bounded 0. They also verified that the effects of the 5-year impact factor is bigger than the Twitter activity, but too imprecise, so it's too broad in comparison to the other ones, and it's not statistically significant. They also looked into the number of tweets and time since publication, and they verified that they significantly impact citation rates. And they also verified that time since publication has a stronger effect than the number of tweets. And also time since publication outweighs both the Twitter activity, so this one and the one in the bottom. And they verified with regards to relative importance that time since publication and the number of tweets have a relative importance of 1.0, whereas the Twitter reach and the 5-year impact factor only have 0.4 and 0.42. And then I believe they ran other 2 separate regressions using only the most significant predictors. They don't really say much about this. They only said they did it. And so I don't know, but to me, this looks like the number of tweets doesn't really impact the citations because of the standard they were like, I don't know. I was very confused with this. It was only an image, so I don't know. And to conclude, they verified that there is indeed a positive relationship between the Twitter activity and the number of citations, but definitely accounting for time since publication was critical because it had the strongest effect on citation rates when compared, for example, with the Twitter activity. They verify that articles with higher impact factors don't necessarily generate more Twitter activity, and they caution against assuming causality. So just because someone tweets a lot about a paper, it doesn't really mean that it's a high quality paper or that will get more citations. And that was it.
Thanks. Very good, thank you. Right, let's talk about some of these things for a minute. I'm going to keep your slides. Let's go in reverse order. So what I suspect, and please correct me, what I suspect is happening, let's talk about this for a second here. They had 4 variables they were interested in.
Yes, so the citation rate is a dependent variable, and they have 4 predictors, which are these 4.
Two Twitter things, and then the journal impact factor, and then time since publications.
Yeah.
So 2 comments. One, note how this multivariate analysis is absolutely critical for something like this. You cannot just look at the correlation between, say, a number of tweets and number of citations or something, because, probably as this shows, older papers that have been published earlier accumulate more tweets and also more citations. It's really not fair to look at the two in isolation without controlling for these other factors. All right, so then they did some analysis and they found two variables that are significantly correlated with the outcome and two that were not. Right, the bottom two were not, the top two were. There's this idea of parsimony in, I don't know, statistical modeling. You often want to build the simplest possible model that explains some phenomenon. And usually you prefer simpler models over more complex models, meaning models with fewer variables and whatnot. Models without quadratic terms if you don't need them, models with fewer variables over models with more variables, and so on and so forth. So what I imagine they did here is they forgot about the fact that they had these other two things that turned out not to be correlated with the outcome. And they said, what if we had only used, we've only modeled the two that we found were correlated with the outcome? How might the results have changed? But the reason for this is, even if these other two are not sufficiently strongly correlated with the outcome, they could still, have some overlapping variance with things that you had modeled that turned out to be significant. These are, skewing maybe towards positive. Maybe if you had more data, you would have been able to detect statistical significance. But that by itself is a rather low bar, and everything is correlated with everything else up to some degree. That's always the case. So they're saying, there's probably some variance that these factors are, taking away from the other ones that are explaining most of the variance, but there's still, some that the other two are taking away. What if we remove them? How might that extra variance be distributed back to the two that turned out to be most significant? So essentially, they're, I guess, redoing that. What I think this is, and this is, by the way, good visualization in general, or style of visualization. You're plotting the estimated regression line as well as the 95% confidence interval for it. They do that here too, if you notice, but it's very narrow. So here they can be very confident that the real value is within that gray area. Here, the real value is also within that gray area, but the farther away they get, the less confident they become, right? So, if you're talking about papers with 300 tweets each, they probably haven't seen many or any in their data, right? And this extrapolation is very low confidence. What this means, right? The closer they are to the left-hand side, they're much more confident, much more narrow confidence intervals here, because maybe this is where most of their data was. Most papers probably had few tweets associated with them, I guess. So when you look at something like this, you look at the slope of this regression line. So I guess here this skews slightly positive. So it's sort of, if you squint at it long enough, you can see that there's some jaggedness to it, suggesting that it's not perfectly horizontal, like the x-axis is, right? So there's some very faint positive slope there, meaning positive correlation, meaning more tweets gives you more citations on average. But at the same time, you really cannot be very confident, especially towards the right end of this distribution. But I think they haven't seen enough data to be confident about the values here.
How do they compute the bounds? Because if you just run LM, it gives you confidence interval for the parameters. It doesn't give you the confidence interval for the predicted values.
Yes. So you substitute the value of the parameter minus 2 standard errors and the value of the parameter plus 2 standard errors, and instantiate the regression to arrive at a, response dependent variable prediction for that value of the input, in this case, say 300 tweets. That gives you this.
Is this not the case then? Now I understand the product better. Can this be the case that some outliers are there on that plot and they should actually do a regression, say for less than 100 tweets, for example, or less than 50 tweets?
Very likely. Do they say anything about this?
They just flight and they don't say anything about the.
Right. So I absolutely believe this, and I would have looked at this if it were me. I would have looked at the distribution of tweets per paper and the shape of that. I would have tried logging it first to see if that fixes it in terms of normality, and then separately, I would have looked for extreme outliers and maybe filter those out or something as being highly unusual and risky.
Because on the paper they say that there is actually a causality here between the number of tweets and the number of citations, but then we look for this plot and actually we don't know if the number of tweets will be influenced positively or negatively because the contents in plots so large.
Correct. Yeah, I agree. That's a fair assessment of this analysis. Okay. Does this make sense? Yes, okay. One more. Okay, one more thing here. This magic keyword came up. The citation rates model is a random variable of a negative binomial distribution. So what this means essentially is, think of it this way. The outcome variable here is counts of things, counts of citations. Okay. Whenever you model counts of anything, usually the standard linear regression formulation is not the legal one, even though I make you use it. So there's several others that are accepted, this being one of them. Negative binomial regression is designed for modeling count response variables. There's another one called quasi-Poisson. There's others. There's subtle differences between them, but the one bit summary of all of this is if you're modeling counts as a response variable, the thing on the left-hand side, do not use LM. The standard linear regression model, use one of these other ones. So, they're doing the right thing here. It's basically what this says. You can try using LM and comparing how the estimated coefficients differ and so on, but this is the more legal one to use. So
If you don't use that, if your data doesn't work, then you don't use the standard.
yeah, so if the thing on the left-hand side is a count of something, count of whatever, so in this case, citations, do not use the standard LM model if you model it.
Okay.
Use one of these other models that are designed for count data.
Okay.
And you can Google for, regression models for count data, and you get lots of things about what are accepted ways of doing that.
Okay.
We often just use LM for the purpose of, describing and illustrating and teaching because it's simpler, but conceptually they're very similar.
But they are still linear regression models.
No, not directly, but they behave and are interpreted similarly in terms of how you interact with them in R, and how you clean your data to model them, and how you interpret the coefficients.
So instead of a line will have something.
I'm not sure how you do this. Yeah, I'm not sure. Yeah. Okay, so that's one. Then this bit here, this is very clever and could not have worked out better. We're actually going to talk about this the rest of today. This is very clever. The one bit here that you should remember is that their argument is, look, we have papers that we have multiple papers that were published in the same journals. We have a number of journals in our data set, and for every journal, we have a number of papers we're looking at. Okay, so this, as it turns out, it's exactly the same problem I left you with at the end of class last time. Because quite possibly, papers from a fancier journal get more citations on average than papers from a less fancy journal. Okay, so really, these observations are not independent in the same way that we had multiple children from the same parents in the previous data set at the end of class last time. Right, so one child of some family is very tall, likely the other kid or kids will also be somewhat tall, right? Similarly here, it's maybe would be unfair to think of all of these observations as fully independent, which is one of the standard assumptions for this kind of regression modeling. Okay? And this happens to be a great way of dealing with that. You're saying there's this inherent nesting or hierarchy that's present in the data. Observations are nested by journal, by multiple papers from the same journal. And I'm doing something to account for that correlation, possible correlation between papers within the same journal in terms of the outcome variables. I'm doing something explicit to deal with that, and this is the right thing to do, or a right thing to do. Okay. And then you can read more about how you specify these mixed effects regression models, and actually I'm going to ask you to do one in a few minutes as well. You can see one in action. Yeah.
They just added this as a variable. That's what they did to take care of.
Essentially, they added this as a term in their regression, but then they used also a different API call. Just like with the negative binomial thing, they use a different API call than LM. Here, they're also using a different API call than LM. To do this kind of mixed effects regression, you need a different R package and a different function.
Isn't this not part of the regression with the negative binomial?
It is. So you could do negative binomial mixed effects regression, for example.
Oh, different dimension.
Yes, and you can combine them into one. Right. And that's maybe what they did, and that sounds like a right thing to do in this case, is what I would have also done. It's not the only thing, but it's a good thing. Elizabeth.
I'm still a little bit confused about how you would encode something that's not a scale. Like the identity of the journal is just like IDs of journal.
Correct. Yeah. So the R package and the whatever modeling framework that you're using for this, it takes care of all of that for you. You don't have to worry about it. In terms of actually specifying this, you would write something like this. So let's say citations is the thing on the left as a function of tweets and age, and I don't know what else in terms of 4 variables, and some nesting, open parentheses, 1 bar journal. They're saying for every journal, there's a random intercept term that you're asking to model. And this can be a factor. It has whatever values, text or whatever, it doesn't matter. And you'll see that when this gets estimated, it doesn't get a coefficient in the traditional sense that you interpret in the same way as you interpret for these other ones. You get traditional coefficients for all these other ones that you interpret in all the same way as before. And you get something else that tells you about the variance that can be attributed to the journal itself.
So it probably like does the normal.
Correct.
For this journal plus this for this journal.
It actually, in this case, it doesn't give you journal level coefficients, but it tells you overall there's this much variance that can be attributed to differences between journals, without telling you specifically kind of what the one journal is versus the others. While we're talking about this, a great point to ask you, what is an alternative specification of such a model? Right, so let's say you didn't know about this mixed effects magic with random intercepts and so on. How else might you still fix this problem that is the same problem I left you with last time. Yeah.
Indicator variables?
Yes, what does that mean?
For each journal, you have a 0 or 1. And, or you have a variable for each journal. And then the coefficient is 0 or 1 based on whether you're in that journal.
Yes. So another way of doing this is to have the same model plus journal as a categorical variable. You know, in the same way we've seen gender and whatnot as a categorical variable. Ultimately, it's exactly the same thing. Okay? So what will happen is, if you do nothing, the one that is alphabetically the smallest will be taken as the reference value. And then there will be a coefficient estimated for all the other ones, all but the reference one. So, you know, let's say you have 4 journals, A, B, C, and D in your data set. A is the smallest, becomes the reference value. You don't see a coefficient for it. You will see estimated coefficients for B, C, and D relative to A, and you can interpret those. You can say, you know, holding everything else constant, journal B gets, you know, this many more or fewer citations compared to journal A. And similarly, the other ones. But effectively, by doing this, you have explicitly modeled and therefore isolated the variance that can be attributed to differences between journals. And you can still model the other stuff you care about that's at the paper level. Okay, so this is called a fixed effects regression because you're using this categorical variable as a fixed effect. All of these other things are also, they happen to be called fixed effects. This is called mixed effects regression because this extra fancy term here that we haven't talked much about until today is called a random effect for journal. And you know, the other ones are still called fixed effects, but together you have fixed with random, and therefore they're called mixed effects models. And now this is fascinating. I don't know if you care enough about this to like go down this rabbit hole, but as it turns out, people are fighting the same kind of fights you see between, you know, like editors and whatnot, text editors and that sort of thing. There's really entrenched ideologies behind these two approaches. I don't remember which community is on which side. I think the econometricians are, you know, pushing for, I don't know, fixed effects everything. They're like, no, you know, the mixed effect stuff is BS. And then some other community, I don't know which, because I don't remember right now, the social scientists or vice versa, I don't know which is which. They're like, no, you know, mixed effects, it's always better. You can do everything you can do with fixed effects and more, you know, you should always use this other approach over the first one. So anyway, so this is really fascinating. People really get like angry about this kind of stuff. Ultimately, in your case, it won't matter. Both are okay, except one caveat. Personally, I prefer the first one, the mixed effects one, for the following reason. Imagine here, you have a categorical variable with lots of possible values. Okay? So, you know, if we have 4 journals, no big deal. But if we have, I don't know, the previous example we used in class was some 200 and some families, I think they were pulling data from. Okay, so that's 200 and some possible values of this. Arguably, this approach is much more annoying than the first one for 2 reasons. One is, for A, you get estimated coefficients for 200 and something minus 1 of those values. So the thing becomes unreadable, just annoying. 2, you actually use up more degrees of freedom to estimate all of these coefficients, meaning you actually need more data to reach similar levels of statistical significance, because now you're estimating more coefficients, in fact, hundreds more coefficients in that case, if you do it that way. So everything else becomes less statistically significant because of this. The previous approach does not suffer from that problem because you're not actually estimating 200 individual coefficients. You're essentially estimating one that does something magical. So personally, I always use the former, but I think the latter is just as correct, technically.
I know you're kind of aligning this for time, but could you describe, like what, like fixed and random, like means?
No, I don't believe I could, even if I had more time. It's not even a matter of time. I think the differences become very technical and very subtle and frankly above my training. Yeah, I'm not a statistician.
Since you're introducing so many more variables, would you be increasing your chance for a type 1 error?
As well.
And that doesn't happen with the other one? That's kind of interesting.
Yes, magic.
I don't think I understand how the first one, the second.
Say that again.
I don't understand how the first one, the second.
Right. So the second one gives you coefficient estimates for all but one of the values of this categorical variable.
Yes, but internally, it's not what the first one will do.
No, internally, the first one will not estimate individual coefficients for
Okay, unless
for each of these
we have
values.
those coefficients plus a distribution that it will sample from.
Yeah, so I think the first one figures out a way to assign some of the variance to variance between journals without estimating for each individual journal how much each one of those is responsible for. Sort of carves out a bunch and says, you know, this is the variance due to journals.
Okay, and every time it gets, okay, it's journal B or C.
It doesn't try. It doesn't try to do that. It just says this is the variance for all the journals combined. It doesn't try to estimate at the individual value.
So how does it?
What
Does it know that it's like journal B or C to assign to the response?
It doesn't. It makes general assumptions about the shape of the distribution of
all the
those
journals.
things. Right. Yes. Which is why it cannot make individual predictions.
And that's why it's not so understandable.
Hungry. Yes. And also doesn't need as much data. Cool. So by the way, either one of these really important kind of thing to remember. Like if you have bandwidth for one thing from today, remembering that you have to explicitly control for the fact that things are nested or that there's hierarchy or that observations are not independent. You have to do something explicit about this. And there's two things you could do, but you have to do something. You must remember from today that you have to do something to fix this problem. Because otherwise, the reviewers will be angry and they will reject your paper. Nobody wants angry reviewers, correct? Okay, good. So with this, let's now play with actual data. I have posted in our wonderful Slack channel. Nobody told me the lights are on. This is unbelievable. Nice. Please tell me if you aren't or don't have access to the Slack channel so we can fix this. But please take a look at this CSV file, download it and load it into R. And let's start by looking at it. So the setup is the following. Imagine an experiment where you're testing a new typing device like a keyboard. And you have a number of participants, I think 50 participants in the study, that are asked to type some text on this new keyboard. And you have measurements of how long or how fast they were typing, how many words per minute they could type or something like that on the one hand, and how many errors or typos they made at the same time. So first question is, what does the relationship, I would like to see a plot, scatter plot or something. What is the relationship between typing speed and typing errors, number of typos in this data set that I shared? Can anybody produce a kind of plot of these two columns in the data set? Right, so to import the CSV file, I recommend using the reader library, or if you're lazy like I am, I recommend clicking on this import dataset button at the top there.
It doesn't have CSV as an option. Should I worry about that? Or-
Say from text with reader, the second option, and then it gives you a menu, and you can point it to the file you want to load, and that should do it. By the way, it also shows you the actual R code it uses to produce this, and you can copy that and remember it for next time, so that you don't have to do this manually in the future.
Sorry, just wondering, what is X, Y, EX, and EY? The column?
Ignore for now. Ignore. Yeah, look at the other ones. The other ones are called typing speed and num typos. These two. Who has a pretty plot to share? Show you have one? Nice. Okay. You want to go? Yes. Yeah, like that. Great. I see more. I will waste no worries. Take your time. Those of you that have produced a plot already, how would you interpret this? You know, what happens when you type faster? On average, overall, how would you interpret this? Yeah, that's good.
What is the numbers?
Right.
Is it like the 2 to -2? What is the rest
This may be fake data,
Okay.
but imagine they mean words per minute or something, maybe standardized,
Okay.
versus errors per minute or something like that. Typos per minute.
So you type faster than you may, you'll have like more errors.
Is that what it says?
Or it was the other way, to be honest with you.
Which is not what I'd expect.
Yeah. Type faster, less typos, according to the data.
Or when you have less typos.
Yeah.
The data set is truthful in many ways. It is maybe randomly generated.
Does that make
but
sense though?
So you're more expert, the more expert you are at typing, the more precise you are.
Isn't that amazing?
It's true of my mom.
I think about it being,
I just think about all these people who can't do keyboard, and then they do their little typing tests. They're pretty precise.
What do you say?
Yeah.
I can
Type faster.
Right, so you could do something as simple as plot function, and then the data set name, like call the data set.
He doesn't make typos, he just does the substitution.
Those make
Words are wrong.
data set dollar, and then the name of the column on the x-axis. So or tab in the column is
More plotting typos, years is no good type.
Is it normal? It is also that it's not what I'm looking for. Each? Actually, I think that is what I wanted. This is super.
Or we modeling things now?
Oh, I just did L11. I just did L11.
We just. There's probably.
Oh, wait, if I just do mod of B, but
Maybe. The CSV and Slack.
oh, I see what you're saying. That's, yeah, okay, like you want.
Yeah.
Oh.
I feel like you jump to the next step, basically. Oh, my scan logic.
Oh, just
Survey
cross
logic.
file.
Very slow choices.
Right.
You can skip
Right, so that should be-
logic.
And then it puts it in some that's page. That's the name of the object. So it's the thing that assigned it to.
Wow.
Use it in the-
I think the coding concept.
Oh, I was gonna say that was actually.
You've seen any cool hats.
Oh, yeah, people started giving.
He has like, really?
Video list.
Oh, no, it's like,
No.
it's like.
Yeah.
People keep getting them.
Then
I did not say collection.
That's pretty cool. They all have like the same style.
Yeah.
Is it one artist or like?
Yeah. People just find questions.
Sweet. Thank you. Do we have a plot? Does anybody not have a plot? Yes, we have a plot. Don't be shy. Yes, yes. Okay. Anybody not have a plot? You have a plot or not? All right, let's. You could do plot typing speed and then dollar. That's it.
How do you change the?
If they-
How do you change?
There. Do we have it? Anybody still not have it? I'm happy to help. You have it? Okay, so interpret this for me. The faster you type, the what you make?
Let's type this out.
True.
Sure it is, it's in the data.
Well, I think if you try to go faster than your average, you'll probably make more typos. I guess that's why it's not intuitive, because whenever I try to speed up, I make more typos.
Ah, so super unintuitive.
Or what I was thinking is if you can type faster, that means you make less typos, and hence you have to correct less, you have to backspace less. And therefore you type faster.
No way anybody types faster and more correctly at the same time. No way.
But it might be that those who type faster has generally less typos.
Ah. Ooh. So now think about what I'm doing here for a second and how much I'm lying to you. There's a participant column in the data set, which indicates that there are multiple observations for the same participant, and presumably there are multiple participants. I think 50 participants, if I remember correctly. You can check how many unique values there are in that column. Okay. So, in other words, in much the same way that, you know, children are nested by family or in families, and papers were nested in journals, we have individual observations of whatever, typing speed and errors, nested within study participants. Yeah. So, as it turns out, if you were to, okay, so one more thing before we do this. Forget about the nesting part yet. Here's a very simple model, typing speed as a function of number of errors. I guess the other way around should have been better, number of errors as a function of typing speed. That makes more sense maybe. In any case, this would show you that relationship or confirm that relationship you've seen in the scatter plot. Okay, so now let's go back and imagine, here's an example. I have pulled from that data you've plotted 5 separate participants, and I have color-coded their observations so you can see them better. So now, if you look at any individual participant, what do you see?
Positive.
When they go
Or very,
faster, they
very
get more
small. Or like either a very small relationship or.
As you would expect, arguably. Okay, so like, you know, if you were to draw regression lines here, which we will not do right now, you would probably see, you know, some slight positive correlation for these that kind of matches the diagonal of these ovals.
Can you show the code you used to do this?
Yeah, of course. It's quite a bit. So first thing, I took out a few participants. I think it's called participant in the file I shared. So for participant in some list of participants, I only take those observations, and then there's some mess to plot it. I'm happy to share this, you know, afterwards. It's not a problem. But there's no need for you to replicate this now. Okay, so what is happening? What's happening is, if we look at any individual in the study, we see what we expect. But if we look at the population as a whole, we see exactly the opposite. Right? We would draw exactly the opposite conclusion. Right? If we look at the population, you see this, you know, negative slope here. Look at any individual, we see positives. So by the way, this is something called ecological fallacy or Simpson's paradox. There's a technical term for this. It's very interesting. This is an instance of that paradox. The paradox is that you draw opposite conclusions from the same analysis, depending on what level of hierarchy or aggregation you're looking at. So, you know, in this case, if we look at the individual level, we would draw the exact opposite conclusion than if we were to look at the group level. Hence the paradox. And this is a known problem in statistics and data analysis, and one that you risk encountering, you know, in your own empirical research as well.
Well, I guess like most things that are called paradoxes are not exactly paradoxical, but like it depends on the question you're asking, I suppose. Like, do you want to know if a random employee who comes through the door who's like faster at typing is going to produce less typos? Or like, do you want to know like whether you should push an employee to type faster than they already do? Like, I guess it just depends on what answer you want to know.
Sure, but you're overthinking it. So at a higher level, you're looking at the relationship between typing speed and errors. And in this abstract sense, depending on how you operationalize that, you know, at the individual level or at the whole sample level, you might conclude different things if you're not careful.
Mhm.
Right? If all you do is sort of look at this at, you know, any one individual level, you would conclude positive. If you look at this at the whole sample level without really thinking too hard about it, you would conclude negative. But, you know, I agree with you, right?
So don't do that thing. Don't do that thing where you don't think too hard about it.
Which is why you're taking this class. Don't do that thing. Don't be that person. Don't be the person. Think hard about it. Okay, great. Excited? Yeah. Isn't this amazing? And this happens all the time in the wild. You don't even have to fake data like I did. It just happens naturally. It's amazing. Okay, so now let's think of some ways of fixing this. This is the thing we started from. The overall scatter plot that you all have. Slightly different data maybe, but it's the same idea. This is, okay, yeah. This is a model that gives you errors as a function of speed. And it tells you that the relationship is significantly negative. More speed means fewer errors. Incorrect, arguably, conclusion. Okay. And the model looks good. You know, if you look at the diagnostics and so on, you're happy. It looks good. No problem there. Oh yeah, here I did actually have it. This is the thing with regression lines at the participant level, color coded. That shows exactly the opposite relationship. Okay, so let's fix this. Okay, show me a regression. Errors as a function of speed that correctly shows this relationship. LM, ignore the discussion earlier about LM being wrong. Just use LM. Try it, show me. Show me a regression, a linear model that correctly arrives at this conclusion. By the way, side note, you know, usually when you're doing this in real research for your PhD and whatnot, you don't usually start with the conclusion you're hoping to show and tweak the analysis until you're able to show that. Just for the record, while we're being on camera, I want to be very clear. Don't usually do that. So summary, LM, errors, I forget what they're called, as a function of speed, plus maybe something. Oh, and then comma. Oh man, the markers are killing me. Data equals whatever the thing is called in your case. A couple of things to help you maybe. A couple of mistakes I've seen, or not mistakes, the issues that make it stuck. The first one is, if you do this, you have to tell it to use the first row as names, because otherwise it thinks the first row is data instead of just headers, and it mixes text with numbers and it messes things up later on. So just make sure you're reading it in with the first row as names as a header. So that's one thing. Let me forward it. Okay, and next, so something like this should do it. Should be sufficient. Next thing I've seen, you can inspect the data types. If you do something like SDR for structure of this thing, typing speed, and if you look at the data types, it tells you that participant is numeric. Okay? And that actually is not useful because we want to treat this as a categorical variable. So we have to fix that. One way of doing that is to say something like typing speed $participant, which is that variable name, becomes as dot factor of the same thing. Okay, so now if I do this and I look at the same thing again, participant becomes a factor with 50 levels. Meaning a categorical variable. Okay. So now you can do what you were maybe thinking of doing. That makes sense? So what's the model? Speed plus participant. Okay, that's approach number 2 from earlier. The one where we model participant as a fixed effect. We get a coefficient for every one of them. Relative to, I'm guessing, number 1. Right, so it probably starts at 2. Is that true? I guess I can confirm that. Summary, LM, what is it called? Num typos as a function of typing speed plus participant data equals typing speed. Okay, so it starts at 2, presumably. Starts at 2 and goes all the way down to 50. That's how many there were. 1 coefficient for every value of this. And it tells you how much different each one of the participants is compared to the first one by convention. On what? On average typos. On the average number of typos.
Sorry, I missed it. Can you show me what line of code this?
Yes, this one. You don't have to do it all in one line. You can, put the LM thing in some object and then call summary on that object.
Adding typing speed to participant because I just have the typing speed with because how does it know that this is you're trying to?
Yeah, so this syntax tells it to estimate the coefficient for every one of the things in this list of things that are written.
Okay, so it's just an overloaded operator. It means different for each.
Correct. In this case, it just means terms in the formula for the model.
But not even an overloaded operator, it's just syntax.
Oh,
It's just a text. Yeah, so this thing here is the formula. Is a formula object technically, which does something. I see. And that's the syntax for specifying that. Okay, it's creating that object.
What does it mean when you see that participant 4?
Participant 4, right. It means compared to participant 1, participant 4 makes on average indistinguishably more or fewer errors. It's as many errors on average. Okay. And the same for the other ones, but importantly, look at the interesting bit here. Positive. The faster you type, the more errors you make. Which makes sense given what you're looking at.
So I think the interpretation may be that if you are the same person, then if you type faster, you will make a mistake.
Correct.
But it's possible for one person or several persons to be very familiar with typing, that they can type very fast and also make some.
Very, very much so. In fact, you see this if we interpret the factors, right? You can see that some participants are make way fewer mistakes, and some participants maybe make way more mistakes than participant 1. But that's what that thing tells you.
I did the same equation.
Yep.
I also get a positive regression coefficient for typing speed.
Yeah.
For my participant, I don't see each one. I just see.
What is it a factor?
I just think this.
If you do, show me the data type for this. You do str for like structure and then boom, str
And type it here.
str. This is the interpreter. You just command take the interpreter, and then copy this in data dot first. Yeah. Right. So that is a number. So basically now it thinks that the value means something, and it just interpolates. It treats this as unit of counts or something. So the thing to do to get what we will get there, or change the data. Here, look, this part here. I'm telling it to treat it as a factor, as a categorical variable instead of a number.
Oh, I was very important in this.
Because the number doesn't mean anything here, it's just an identifier. Like, it's not an actual count of anything, not a variable, it's just an identifier. It could have been a string for all we care.
Okay, and so you do that before, yeah, okay.
And I do that before I model,
Before you know.
otherwise it doesn't know. Similarly, you could do it directly in the model. You could put this thing directly in the model formula around that variable participant. That would be the same.
Okay.
Before you were showing us a plot with lines.
Yeah.
How does that relate with this?
Yeah, great. I'll show you the plot with lines again. So, controlling for participant, which is what the factor does. Controlling for participant, there's a positive correlation between typing speed and number of errors, meaning the faster you type, the more errors you make. So this is basically this. The faster you type, the more errors you make. The faster you type, the more errors you make. Controlling for participant, the faster you type, the more errors you make. So basically, we're estimating this line, any one of these lines actually. Yeah. Yes.
Make sure that I'm reading the participant, like on the.
Regression?
Yeah, yeah.
Yep.
The coefficients correct?
Yes.
So if like participant 2 has negative coefficient, does that mean that in their situation they are faster or they're more accurate when they're faster, or?
Well, controlling for speed, everything else stays constant. At the same speed,
Oh, they make fewer mistakes.
they make fewer mistakes than participant 1 on average.
Yeah, oh, okay, okay, that makes it more. Thanks. Oh, so this is all compared, they're all compared to the baseline, like to the previous first.
Compared to the baseline, the default value of the factor variables, which in this case happens to be the one that's smallest alphabetically by convention. Or you could change that. You could set the different defaults. In fact, you could do this in a number of ways, and maybe we should spend some more time talking about that. You could set this to be, for example, the overall mean across all of the values. And then you would have a coefficient for all of them, including participant 1, relative to the global mean.
Okay.
For example, that's one thing you can do.
That was
And that-
nice.
that's another thing you can do. Okay.
So the new regression line will be the average of all those regression lines that we see.
This regression line,
Combination of those lines.
this regression line is an average of all of those regression lines, correct? Average slope of all of those regression lines. In fact, yes, in fact, it is assumed that they all have the same slope here, the way you're doing it. Because the participant only changes the mean value, and then the slope is constant, is defined by this coefficient. All of those lines you assume have the same slope, and this is the value of that slope you're estimating from the data. Okay, so strong assumption that they all have the same slope. Yeah. Okay, so give me 5 minutes to show you a few more things on this note. Yeah, please look at what I'm showing you if you're distracted doing something else. Okay. So this is what we've just seen. It's what we've just seen as the factor for the participant. And in this case, I sampled a few of those. I didn't keep all 50 in here, but it's sort of equivalent. Okay, this is interesting. So here's how we would do the same thing, except now using this mixed effects regression instead of the fixed effects one. I say, the observations are nested by participant. This is called something else. It's called participant in your CSV file. Here's full ID. Forget about that. Observations nested by participant. And I call, where's the formula? Where's the code? The code is something else. It's not LM, it's something else. It's Elmer in this case, for whatever reason. So it's going to be a different API. Like this, Elmer instead of LM. The Elmer one works with this random effect thing, and you need to import some library, maybe LME4, I think.
Yeah.
LME4, linear mixed effects 4 is the library to make this work. But otherwise, this is sort of equivalent. And so here's what you get. You get a coefficient for speed, much in the same way that can be interpreted in the same way to the one we had before. And you can compare the estimates also to see how they differ. And you get some amount of variance that gets attributed to differences between participants, which is this much. And it also tells you how much variance is left, the residual variance, which is this much. So note how it doesn't give you a coefficient. That's the important difference. It doesn't give you a coefficient estimate for each participant individually. It just tells you overall this much variance goes to differences between participants. I think this might actually be the variance of the mean values of all of the participants in the sample. And that's what's left. And this is how so speed explains the relationship there. Okay, so here it gets super interesting, I think. Note how neither of the ones we saw already, the fixed effect one or the mixed effect one, showed you both patterns at the same time. Like the simple thing we did in the very beginning showed negative correlation, right? Faster speed, fewer errors. Either one of these two things we did afterwards showed you positive correlation for individual level, but nothing so far showed you both patterns at the same time. Do you agree?
Yes.
We were not able to model both these sort of within subjects positive correlation as well as the between subjects negative correlation all at the same time. It turns out we can if we're being a little clever. So the cleverness here is decomposing, basically changing the data a little bit. So what I've done is, instead of speed as encoded originally, I create two different things. One is the mean value for every participant of their speed, which is this thing, okay? Mean of speed by participant. And then the second is whatever's left, the difference, right? Because people don't just type at their mean speed, right? They type faster or slower, right? So the error term is whatever's left, from actual observed speed relative to each individual's mean. Okay, so this one gives you within subjects variation. This one gives you between subjects variation. Okay. So now I redo my regression. Okay. In this case, I kept the random effects one, but we could have done this with fixed effects, maybe. Homework for you to figure it out if you could have done that. And I use the two new speeds instead of the previous one. And this gives you too big. There we go. Between participants, the faster they type, participants who type faster on average make fewer mistakes. Right? But on average, participants who type faster on average have higher mean typing speed on average, make fewer mistakes. Okay, forget about the p-value because I'm not actually modeling the whole data set. I'm only modeling the sample. So forget about it being not significant. And similarly, within participants, individually, when somebody types faster, they make more mistakes. Everyone, including the experts. Okay, cool. Okay. So now, right, we talked about this. To Luis's question earlier, the assumption in everything I've shown you is that the slope of all of these lines within participants is the same, which is a strong assumption. Okay, so it turns out we don't have to make this assumption. You can actually model different slopes as well, which is why this mixed effects framework is nice. You can model differences in slope by participant. Cool.
Why do you still need the speed
Because the speed in front is the fixed effect for speed, and the speed in the thing is the random slope, and there's something else.
But if we do this within the normal LM, then we don't need the speed in front.
You can do this in normal LM. The syntax is not allowed.
I know, but if you try to do this like by having a interaction between speed and ID,
yes,
then you don't need the first initial speed.
Correct. Yes, I think that's right. I think what you're saying is right. Okay, so let's say you do this. You're testing for difference in slope, and you look at how much variance is attributed to these. So look, variance by participant, 10 units of whatever this is. Variance variance attributed to difference in slope, 5 times 10 to the minus 5, super tiny compared to the other one. So this is 10-ish. It's 1 times 10 to 10 to the power 1. Scientific notation, yes? Mm-hmm. This is 5 times 10 to the power minus 5. So relatively tiny. Fair to conclude, by comparing these, that hardly any variance is explained by differences in slope between participants. So to Luis's question earlier, maybe the slope being the same between participants is okay here, as it turns out. But you don't have to make that assumption. You can actually test for this. That makes sense? Okay, so now challenge for you. And I promise I'm finishing. Back to this. Assume I've decomposed speed into average speed for participant and whatever's left. Could I have modeled this with fixed effects? So having the factor for participant instead of this random effect for participant. Yes or no, and why? Why not? So in other words, could I say LM errors as a function of speed M plus speed E plus factor participant. Data equals whatever. Could I have done that? Yes or no? And why not?
Between speed within the participant, mean speed of the participant and the participant factor.
Yeah. Yes, correct. So the answer is no, probably. Because speed m will capture the same thing as participant factor captures. One value per participant. There's no variation in speed m within participants. They all have the same mean value. Which is the same as including the participant fixed effect. Which does the same thing. Captures the mean speed for that. Does that make sense? You see what I'm saying?
How do they have the same mean speed?
Yeah, okay, yeah, I'll show you. So, yeah. Right, here's an example. Participant 1, with these values of speed that are all different for participant 1. When I decompose that into mean and whatever is left over, obviously the mean is the same within participant 1 because it's their mean. And whatever is left over is whatever is left over. Right? So now if I model these two things here, and I separately have a categorical variable to capture which participant it is. This thing here uniquely identifies the participant already. So then the factor doesn't work in that case. You can't, the two together don't make sense. They do the same thing.
Unless you have a participant that just coincidentally happens the exact same.
Right, right. Very good. Yeah, good job. So now I claim that you're ready. I think your next submission is going to be bulletproof. I think I've mostly taught you everything you need to know to do solid regression analysis and not make your advisors angry and not get the reviewers to reject your papers. If you're comfortable with what we covered these last 2 or 3 lectures, you're golden, I claim, for real. Okay, so it's not too much, I think. But it takes a bit of practice to become fluent with interpreting and modeling choices and so on. But roughly, this is all there is. Everything else is syntactic sugar and fluff, which you can figure out as you go along. The negative binomial thing, sure, you figure out that you should use a different class of model, but then everything else stays the same, and how you think about it stays the same. But sure, you call a different API, fine. Right, all the other stuff you figure out as you go along. But if you're comfortable with interpreting what these things mean, you're golden. Promise. Go do great science now. You're ready. You have arrived. Congratulations. It's very exciting.